pointing away from the sun like a rebellious teenager. But then there's this inner coma quirk. Initially mistaken for an anti-tail, it turned out to be a sunward dust plume, blasting material toward our star due to intense localized heating on the sunlit side. By early September, that inner region had morphed into a fan-shaped structure, evolving faster than any comet we've clocked in our backyard. This rapid transformation isn't just visually stunning, it's a goldmine for data, allowing scientists to probe the nucleus's secrets. The James Webb Space Telescope's readings revealed a surface dominated by carbon dioxide ice, with a CO2-to-water ratio of 7.6.1, wildly higher than the puny fractions in solar system comets. This explains the premature activity. CO2 sublimates at much lower temps, kicking off the show while water ice stays snoozing beneath a thick, insulating crust. It's like the comet's wearing a cozy blanket that traps its watery heart, only letting the dry ice party out early. This composition screams, foreign visitor. The narrator speculates it formed beyond its home star's CO2 ice line, a chilly frontier where dry ice condenses easily, farther out than our own system's setup. Add in the very large telescope's detections of cyanogen ions and nickel vapor, common enough, but sans the usual iron sidekick, and you've got a recipe for endless what-ifs. That flips the script on formation histories, suggesting 3I Atlas brewed in a metal-poor environment or underwent some wild processing en route. The depletion in carbon chain molecules like dicarbon, C2, further amps the intrigue, painting a picture of a comet that's chemically stripped down compared to our locals. These elements don't just spark curiosity, they challenge core assumptions about how planetesimals form across the galaxy. Why does this interstellar drifter look like it shopped at a different cosmic supermarket? It's the kind of puzzle that could rewrite exoplanet chemistry textbooks. Polarization observations from the Nordic Optical Telescope add another layer of cool weirdness. The comet shows an ultra-deep, narrow negative polarization branch, light waves aligning in funky patterns that scream, unique dust mix. Lab sims suggest a thin water ice frost over dark, tarry grains could mimic this, echoing traits in distant trans-Neptunian objects like Pluto and Charon. Tying this to Oumuamua, the first interstellar scout, possibly a nitrogen-iced Pluto fragment, fuels speculation. Is 3I Atlas another chunk from a rogue dwarf planet, hurled from its system's outer edges? The transcripts nod to Oumuamua's pancake shape and pure N2 vibes, makes this feel like a sequel in the interstellar oddball saga. Trajectory backtracking via Gaia's data shows it's wandered undisturbed for at least 4 million years, potentially billions older than our solar system, or maybe just 3 billion per fresh estimates. Pristine or not, it's a time capsule from another star's youth, untouched by stellar drama. These highlights, the hyperactive coma, CO2 overload, missing metals, and polarization quirks, make 3I Atlas a tantalizing enigma. It's not just data. It's a story of cosmic migration, reminding us how puny our solar system's sample size is. As it hurtles inbound, promising invisibility behind the sun by October 2025, the excitement builds. But amid the wonder, controversies lurk, like the head-scratching green glow we'll unpack next. If painted 3I Atlas as a cosmic showstopper, the flip side reveals a hotbed of head-scratching debates and outright clashes that have astronomers and headline chasers at each other's throats. The transcript doesn't shy away from these flashpoints, turning what could be pure awe into a reminder that science thrives on friction. That emerald green hue captured in Namibia's skies during a lunar eclipse, a stunning photo by astrophotographers Michael Yeager and Gerald Riemann that dropped jaws but raised hackles. Old hat for solar system stalwarts, thanks to dicarbon, C2 molecules getting zapped by sunlight into a verdant light show. But here's the kicker. Spectroscopic data from James Webb screams dicarbon deficient. No C2 means no green, or so the rules say. Yet there it is, shining like a lime in the void. This mismatch isn't just puzzling, it's a full-blown controversy that split the community and fueled tabloid frenzy. Enter Avi Loeb, the Harvard firebrand who's made a career out of interstellar eyebrow raisers. Remember his Oumuamua as aliens pitch? In a recent Medium post, Loeb doubles down, claiming the green stems from cyanogen ions, the same cyanide radicals VLT spotted swirling in the coma. It's a bold swing, tying into his narrative of extraterrestrial oddities screaming, "Not from around here." But the transcript torches that idea with surgical precision, calling it very incorrect. Mostly violet at 387 nanometers, dipping into ultraviolet territory with faint blips at 420 nm and infrared. No green in sight. The narrator drops a 1994 paper bomb, the cometary fluorescent spectrum of cyanogen, which lays it out. CN doesn't paint comets emerald, it whispers in purple. Press outlets and websites piled on the error, misquoting spectra like a game of astronomical telephone. Sloppy journalism meets Loeb's flair for drama, critics say. Detractors argue it's emblematic of his pattern, prioritizing spectacle over scrutiny, turning data into clickbait. They see it as healthy speculation, pushing boundaries where timid peers stall. Either way, as of September 2025, the green mystery lingers unsolved, a Rorschach test for how we handle interstellar curveballs. Is it some exotic carbon variant, forbidden dicarbon hiding in shadows, or lab-unknown fluorescence from alien ices? The debate rages in Archive preprints, with teams scrambling for follow-up spectra before the comet ducks behind the sun. This color conundrum bleeds into broader beefs over composition and origins, where 3I Atlas's quirks challenge sacred cows. Take the CO2 overload. That 7.6.1 ratio to water is galactic heresy. Solar system comets tip the scales at trace CO2, formed in our star's warmer nursery. But 3I Atlas, it screams formation beyond a foreign CO2 ice line, implying a parent system with a beefier frost line, maybe a dimmer star or wonky disk dynamics. Cool hypothesis, but controversial as hell. Skeptics point out we lack baselines for exostellar chemistry. Extrapolating from our Oort cloud feels like comparing apples to quasars. In our comets, the duo's a package deal from chondritic precursors. It could flag a low metallicity birth. Think metal-poor stars in the galaxy's boonies, or post-ejection processing like radiation stripping. But purists cry contamination. Maybe VLT's resolution missed faint iron lines, or the insulating crust hit it. The transcript leans into this as bizarre, but forums buzz with accusations of overhyping anomalies to snag grants. One thread on AstroBetter even dubs it Loeb-adjacent sensationalism, linking back to his green gaffe. Polarization piles on the pylon. The Nordic Optical Telescope's deep negative branch is freakish, narrower and sharper than Oumuamua or Borisov, hinting at a dust cocktail of icy frost over soot-black grains. Labs replicate it with water ice veneers on dark organics, but tying it to trans-Neptunian objects like Pluto? That's where tempers flare. Proponents, echoing a fresh Oumuamua study, pitch 3I Atlas as a Plutoid ejecta, a dwarf planet chip from another system's Kuiper Belt analog, complete with nitrogen vibes and pancake potential. It fits the pristine interloper trope, but naysayers scoff. Polarization's too finicky for such leaps. Similar signals pop in TNOs, sure, but correlation ain't causation. Critics like Alan Fitzsimmons argue it's cherry-picking, without direct imaging of the nucleus, obscured by coma chaos. It's fanfic astronomy. A September Gaia-backed paper pegs it at billions, undisturbed for 4 million years, maybe 7 billion old. But a counter-study whispers 3 billion, citing trajectory wobbles beyond that window. Old-timers say it's ancient ice from a dead system. Youngsters counter with recent ejections from active disks. No consensus, just volleys in Nature astronomy letters. These controversies aren't petty. They expose science's growing pains with interstellar refugees. With only 3 under our belt, Oumuamua, Borisov, now this, every datum's a battleground. The transcript nods to press pitfalls like green cyanide myths, underscoring how hype warps public perception. Loeb's post, for instance, went viral on X, spawning alien memes while pros fact-checked in vain. It's a microcosm of 2025's info wars. Rapid discovery meets slow verification, amplified by blogs and bots. Yet amid the squabbles, silver linings emerge, debate drives deeper dives, like the looming coronal mass ejection (CME) showdown. Late September projections had a solar burp barreling toward 3I Atlas, promising to zap its ices and dust for never-before-seen reactions. By October 2, 2025, right on cue, early reports from Soho and Stereo hint at the hit, with Coma brightening oddly. Martian orbiters might snag bonus views as it swings close, but if it shreds, poof, controversy's unresolved. This tension between wonder and wrangling makes 3I Atlas more than a rock. It's a mirror for our quest. As we stitch together the thrills and tussles of 3I Atlas, one truth crystallizes. This interstellar comet isn't just a fleeting visitor. It's a catalyst, forcing us to confront the galaxy's diversity head-on. The best bits, from its hyperactive CO2-fueled outbursts to the polarization whispers of Plutoid heritage, dazzle with promise, painting a portrait of a solar system unlike our own. Yet the controversies, the green enigma, Loeb's cyanide misfire, the iron absenteeism aren't roadblocks. They're rocket fuel, exposing gaps in our toolkit and egos in the observatory. Together, they underscore a pivotal shift. With interstellar objects now a trickle, 3 and counting, we're graduating from passive stargazers to active interrogators of alien archives. This synthesis isn't tidy. It's messy, exhilarating, and quintessentially human, blending awe with argument to propel discovery. Zoom out, and 3I Atlas's standout strengths reveal a broader boon for planetary science. It's a Rosetta Stone for exoplanet atmospheres. Our solar system's comets are water-heavy relics of a wetter formation epoch, but this dry ice darling suggests parent systems where carbon ices ruled the roost, perhaps around M-dwarfs with tighter habitable zones or disks starved of oxygen. The insulating crust trapping water below evokes super-volatile stratigraphy, layers of CO2 shielding H2O like a cosmic thermos. This could explain why some exoplanets boast CO2-rich envelopes without the water vapor we'd expect. Tie in the dicarbon drought and nickel solo act, and you've got a chem lab from a low-metallicity nebula, where iron got gobbled by silicates or zapped by radiation. These aren't quirks. They're clues to galactic chemistry gradients, hinting that our sun's bounty of metals is the exception, not the rule. If life needs water, how do CO2 Comet seed worlds? The transcript's nod to formation beyond a foreign ice line amplifies this, suggesting 3I Atlas as a fossil from a system's outer nursery, pristine, per Gaia's 4 million-year backtrack, yet young enough, 3 billion, to dodge total cosmic weathering. The controversies, meanwhile, sharpen our skepticism, turning potential pitfalls into pedagogical gold. Beyond Loeb's flub, now meme fodder on X, with mere cyanide comet trending amid debunk threads, it's a masterclass in spectral humility. Dicarbon's absence should nix the hue, yet there it glows, possibly from undetected C3, tricarbon, or exotic fluorescence in CO2 ices under solar UV. Our solar system-biased models falter against interstellar variety. Loeb's pitch, while off-base, sparks vital debate. Critics like the transcript's narrator guardrail against hype, citing that 1994 CN paper as gospel, while fans argue it democratizes science, drawing public eyes to underfunded scopes. The iron void stirs similar soul-searching. Is it a true anomaly or observational artifact? VLT's limits mean we crave Hubble or JWST deep dives, but the Coma's veil thwarts them. Polarization feuds echo this. Pluto-Link fans see a family resemblance in frost-dark dust, but data purists demand nucleus snapshots. These clashes aren't chaos. They're calibration, reminding us that with interstellar flybys rare, next one's years off, we can't afford echo chambers. As one September Archive reviewer quipped, 3I Atlas isn't alien, our assumptions are. Looking ahead, the comet's arc bends toward revelation, even as it vanishes. That coronal mass ejection? On October 2, 2025, it struck true, per Soho feeds, a plasma belch slamming the coma, sparking a brightness spike and tail kinks that scream, Interaction jackpot. Early stereo A glimpses show dust grains ionizing wildly, potentially unmasking trapped volatiles, maybe that elusive iron or dicarbon ghosts. Martian sentinels like Maven and Hope Orbiter, with 3I Atlas grazing at 0.5 AU, could relay UV spectra by mid-month, probing how solar wind scours alien ices. If it holds till perihelion, January 2026 reemergence, will eye a transformed beast. Crust cracked, water unleashed, colors cycled from red oxidants to icy whites, as August-September shifts foretold. 50-50 per models, disintegration would echo Borisov's tame fade. But with CO2's volatility, it might puff into a debris fan. Either way, it's a lab rat for space weathering. How do interstellar bits acclimate to Sol's fury? For XAI's ilk, scanning cosmos for signals, 3I Atlas bolsters the natural oddity case against ET hype, yet its quirks, pancake potential, nitrogen echoes, keep doors ajar. NASA's budgeted $50 million for interstellar hunters post-Oumuamua, now eyeing Vera Rubin scopes for early warns. Publicly, it demystifies the stars. Green pics go viral, sparking kid coders to sim trajectories. Controversies humanize heroes. Loeb's gaffes make him relatable. The narrators take down a win for rigor. Ultimately, 3I Atlas embodies the best and worst of us, curious, combative, cosmic. As it slingshots out trailing unanswered whys, it leaves a legacy. Our solar system's not a mold, but a starting point. In a galaxy of billions, this comet whispers, "You're not alone in weirdness." Tune in come December, the encore awaits. A comet just erupted near the sun, its brightness leaping overnight, tail fanning wider than 5 full moons. Days later, the sun unleashed its mightiest flare in months, blasting a massive wave straight toward the spot in space where Comet C 2025 R2, Swan, as the title says, is now heading toward Earth fast. On October 21st, Swan will glide closer than ever, just as another interstellar object passes in near-perfect alignment. With solar storms set to slam into the comet's giant tail, no one knows what's about to unfold. Will the sky light up with drama or vanish into silence? The chain reaction has begun. So what happens when Starfire meets Cosmic Visitor? September 12, 2025. Comet C 2025 R2, now simply called Swan, rounds the sun at a distance of just half an astronomical unit, closer than Mars ever comes to Earth. At first, the numbers seem routine. A faint, slow riser, magnitude hovering around 7.4, tail stretching a modest 2 to green across the night. But comets are built for surprise. Just 2 weeks past perihelion, the glow jumps. September 26th. Amateurs in Japan and Australia catch the first signs. A sudden leap nearly a full magnitude pushes Swan into naked eye territory for those under dark skies. By the end of the day, international forums are buzzing with live photometry, confirming a brightness surge to 5.7, then holding near 5.8 through September 28th. This isn't just a statistical blip. Outbursts like this point straight to the nucleus, a frozen core battered by centuries in deep space now hammered by solar heat. As the comet swings out from its closest solar pass, volatile pockets buried beneath the crust reach a breaking point. Gases burst through, carrying dust and ice with them, swelling the coma and feeding the tail. The effect is immediate. Light curves deviate from predictions, and every fresh observation becomes a clue to what's happening below the surface. Thermal stress, venting, even local collapse all are on the table. Some observers spot hints of jet-like features near the nucleus, possible evidence of crustal fractures or new vents opening up. The comet's behavior diverges from the standard playbook, drawing the attention of both professionals and a global network of backyard astronomers. For now, the numbers are clear. Swan has entered a new phase. Its inner engine exposed, its next moves unpredictable. The question is not just how bright it will get, but what the unleashed energy will do to the comet's structure and to the vast tail now unfurling behind it. A tail stretching more than 2 1/2 across the sky, 5 full moons laid end to end. For skywatchers, that scale changes everything. This isn't just a fuzzy dot lost among the stars. It's a structure you can trace with binoculars, a streak that demands attention even in suburban skies. The sheer span means more of the comet's secrets are on display. Knots of dust, shifting rays, and the faint electric blue of the ion tail, all shaped by the solar wind. The tail's architecture tells a story in real time. Dust, heavier and slower, lingers close to the comet's path, forming a broad sunlit fan. But the ion tail, lighter and more volatile, can snap, ripple, or even break away under the right solar conditions. With Swan's tail now covering a chunk of sky wider than any city skyline, even small telescopes can pick out structure, streamers, kinks, and sudden bends. For observers tracking night to night, the changes aren't subtle. A single evening can reveal a new twist, a fading plume, or a sudden brightening as fresh material streams out from the nucleus. The global comet community is already responding. Amateurs across continents are stacking exposures, comparing notes, and sharing time-lapse sequences that reveal tail motion hour by hour. Forums light up with reports of subtle color changes, icy blue for ions, golden for dust, hinting at the complex chemistry at work. The comet's position low in the southern sky for much of September and October favors observers from Australia, South Africa, and Argentina. But even northern latitudes get a shot as Swan climbs higher and the moon wanes. For anyone with even a modest pair of binoculars, the next few weeks offer a front-row seat to a live experiment in solar system physics. The tail's reach means more than spectacle. It sets the stage for what happens when the sun sends its own shockwave into the same quadrant of space. The question becomes not just how long the tail will grow, but how it will react when the solar wind arrives. September 28th, at 8:43 Coordinated Universal Time. The sun erupts with an M6.4 class flare, its strongest in months. For most of September, solar activity had been unremarkable, with X-ray flux readings from the GOE's satellites trending flat, hinting at a lull in the current cycle. Then, without warning, the X-ray monitors spike. The flare's energy output, measured in the millions of kilowatts, lights up the GOES 16 and GOES 18 charts in near real time. Solar physicists at the National Oceanic and Atmospheric Administration's Space Weather Prediction Center scrambled to assess the event, cross-checking with the Solar Dynamics Observatory. Imagery and coronagraph data from the Solar and Heliospheric Observatory. This is not just another solar hiccup. M-class flares are mid-tier on the scale, but an M6.4 is enough to catch the attention of satellite operators and space weather forecasters. The flare's origin, active region 4232, a complex sunspot group with a twisted magnetic field, places it in the same quadrant of the sun that Swan is now approaching. Within 30 minutes, coronagraphs confirm the launch of a coronal mass ejection. The CME's initial speed, estimated between 800 and 1,000 km/s, puts it among the faster eruptions of the year. Inside the operations rooms, alerts ripple out. Satellite teams double-check protocols for radiation spikes. But this CME is not Earth-directed. Instead, the focus shifts to what lies in its path. The timing, just 2 days after Swan's outburst, draws immediate notice. Duty officers flag the event for Comet scientists, who begin modeling the possible intersection of the CME with Swan's expanding ion tail. For now, the numbers tell the story. An M6.4 flare at 0843 Coordinated Universal Time, a CME racing outward, and a comet with a tail more than 2 degrees wide in the line of fire. The sun, quiet for weeks, has sent a powerful pulse into the same sector of space where Swan is putting on its own show. The intersection of these events is rare, and every instrument, from GOES X-ray detectors to ground-based telescopes, now has a reason to watch closely. Inside the NOAA Space Weather Prediction Center, the race began as soon as the flare peaked. Analysts pull up real-time feeds from SOHO's LASCO coronagraph and Stereo A's heliospheric images, combing through frames for the expanding arc of plasma. The CME launched just after 0845 UTC, fans outward with an initial speed near 900 km/s, fast enough to cross the average Earth-Sun distance in less than 2 days. Its angular width, measured at approximately 90 degrees, places it among the broader ejections of the year. But the crucial detail was its aim. This time, the blast misses Earth by a wide margin. Instead, model overlays show the main lobe sweeping into the sector of space now occupied by Comet Swan. For the forecasting teams, the challenge was geometry. Solar ejections don't travel in perfect straight lines. They expand, twist, and sometimes fragment as they plow through the solar wind. To chart the CME's path, scientists stitch together coronagraph images, plotting the leading edge against the known positions of planets, spacecraft, and for the first time in years, a comet with a tail longer than 2 degrees. Swan's coordinates, just inside Earth's orbit and slightly south of the ecliptic, put it near the predicted corridor, but the three-dimensional uncertainty remains. Without a direct Earth hit, in situ plasma data would be limited, leaving ground-based and orbital imaging as the best tools for tracking the encounter. Every major forecast center flags the event for comet researchers. The question, would the CME's broad front actually intersect Swan's tail or sweep harmlessly past? The best estimates place the CME's arrival in the comet's vicinity between 48 and 72 hours after launch, depending on the true trajectory and speed. Density projections suggest a moderate event, enough to disturb the ion tail but unlikely to trigger any terrestrial effects. For Earth, the risk was minimal. For Swan, the incoming solar plasma sets the stage for a possible display of tail kinks, disconnections, or rapid changes, phenomena that could unfold on timescales of hours, visible to anyone watching the right patch of sky. The tools were ready, the data streams open. Now all eyes shift to the comet corridor. Magnetic fields shape the fate of every comet tail caught in the solar wind. When a coronal mass ejection like the one launched on September 28th sweeps across space, it drags with it a tangled web of magnetic field lines, each one carrying its own orientation. The ion tail of a comet is built from charged particles, stripped from the nucleus and pushed away by the sun's constant outflow. These ions don't just drift. They cling to magnetic field lines, forming a kind of invisible tether stretching millions of kilometers behind the comet. But the real drama begins when those lines meet the boundary between the comet's tail and the incoming solar wind. If the magnetic field embedded in the coronal mass ejection points southward, opposite to the typical direction near the comet, conditions are ripe for what physicists call magnetic reconnection. This is the cosmic equivalent of a circuit breaker snapping open. Field lines from the solar wind and the comet's tail collide, snap, and rapidly rejoin in new patterns, releasing energy and cutting loose whole sections of plasma. In practical terms, this means the comet's tail can break away in minutes, sending a glowing fragment drifting off into space, while a new tail begins to form almost immediately. The orientation of the coronal mass ejection's magnetic field, especially the BZ component, determines the strength of this effect. Southward BZ is the trigger most likely to sever the tail, while northward fields can slip by with little more than a ripple. The process is fast, sometimes visible within hours, and can leave behind dramatic kinks, sudden brightness drops, or even a detached cloud of ions moving independently. For theorists and modelers, this is a rare chance to see magnetic reconnection play out on a scale no laboratory can match. With every twist and break written across the sky in real time, every hour now counts. The window for dramatic change is open, and the rules are simple. Watch the tail, trust what you see, and keep your expectations nimble. Swan's ion tail, more than 2 degree long, is exposed to the full force of the solar wind. If the CME's magnetic field lines intersect the comet's path, the ion tail could kink or snap away in as little as 90 minutes, a process that for most comets unfolds quietly in deep space but now plays out on a stage visible to backyard telescopes. Spectral signatures may shift abruptly, with hydrogen and oxygen lines drifting by up to 50 km/s as the plasma reacts to the shock. Morphology can change on timescales shorter than a movie, with a bright filament breaking free, or a new tail forming in the wake of a disconnection event. This is science at real speed, and the best data may come from citizen scientists, anyone with a camera and a clear sky. But caution is essential. Not every ripple or sudden dimming is proof of a solar storm. The geometry of the CME's path is still an open question, and predictions about direct encounters remain hypotheses, not established fact. Experts urge vigilance, not certainty. The correct response is to document, compare, and report, building a global record as the comet's story unfolds. For now, the only guarantee is change. The next anomaly could appear in a single frame, and the world is watching together. October 21st, 2025. The numbers tell the story. Swan will pass just 0.25 astronomical units from Earth, about 39 million kilometers, or roughly 100 times the distance to the Moon. For a comet, that's the planetary equivalent of a close flyby. This isn't a random approach. The geometry lines up almost perfectly. Swan's orbit crosses the ecliptic at a shallow angle, riding the same invisible plane that defines the solar system's main traffic lane. The comet's position just south of the ecliptic places it squarely in the zone where the solar wind and heliospheric current sheet are most active. On the same date, interstellar visitor 3I Atlas reaches superior conjunction directly opposite the Sun from Earth's perspective, while Swan sweeps through its closest point. Both objects, separated by millions of kilometers but sharing the same broad corridor, offer a rare chance to compare native and interstellar dynamics side by side. For orbit analysts, this alignment is a statistical outlier. The odds of two such bodies, one from deep solar orbit and one from interstellar space, converging near the ecliptic within days are vanishingly small. The timing is just as striking. October 21st brings a new moon, erasing lunar glare and creating the darkest skies of the month. With Swan at its nearest, the parallax effect, tiny shifts in apparent position as seen from different points on Earth, becomes measurable to even modest backyard telescopes. Sky position plotting shows Swan climbing higher each night, its tail tracing a path across the southern constellations. The gap between Earth and the comet, mapped in real time, shrinks to a mere quarter of the Sun-Earth distance, offering the best possible window for observation before Swan recedes into deep space once more. For anyone hoping to catch Swan in the coming nights, timing and preparation are everything. October 21st is the headline date. Closest approach, new moon, and the darkest skies of the month. But the window stretches wider. Swan's path runs just south of the ecliptic, climbing higher each night through the southern constellations. From Buenos Aires to Perth, the comet rises early and lingers well into the pre-dawn hours, its tail sweeping west across the horizon. In northern latitudes, the view improves as October unfolds, with Swan peaking above the tree line after midnight and gaining altitude each night. Star charts put Swan near the border of Grus and Piscis Austrinus. Easy to find if you trace a line from Fomalhaut to Achernar, the brightest star in the region. The tail's orientation favors a side-by-side comparison with field stars. 212 degree long means the comet's trail can be measured against the gap between Fomalhaut and its nearest neighbors. For binocular users, a standard 7x50 field of view covers the entire tail in one sweep. Small telescopes reveal more detail, but even a camera on a tripod can capture the streak with exposures of just a few seconds. The parallax trick comes into play as Swan closes in. With the comet just 0.25 astronomical units away, its apparent position shifts ever so slightly depending on where you stand, an effect measurable with a few hours' patience and a careful eye. Amateur imaging crews are coordinating across continents, logging rise and set times, and sharing overlays to track the tail's nightly changes. The checklist is simple. Note the comet's position, sketch or photograph the tail, and watch for kinks, sudden brightenings or fading. Every observer, whether in city glow or rural dark, adds a pixel to the global picture. This is the moment to join the watch. This rare timing sets up a documented encounter. As Swan nears its closest approach to Earth on October 21st at approximately 0.25 astronomical units, scientists are watching for direct effects between the CME and the comet's ion tail, a phenomenon known to cause rapid visible changes. However, The exact outcome of this solar-comet interaction remains unproven, and no direct link has been established between the recent solar flare and Swan's earlier outburst. What is verified this October? Both amateur and professional observers have a unique window to witness cometary and solar dynamics in real time. As documented in the Global Observation Campaign, Swan's journey is a rare opportunity to track cosmic forces at work, with key results still unfolding.